Okay, so this is the last video. Um, yeah, literally, this is the last video. So we are in Mod 5, and this is the second half of Mod 5. The first half of Mod 5 covered all of this non-parametric basic stuff that we're continuing on, and then this is it. There's nothing else to learn. Well, there is, but not in this course. Um, so non-parametric stats are sort of like special techniques for using when you can't use regular statistics is a good way to describe them, including when you have small sample sizes, which is the one valid reason to keep this in this course because psychology people can possibly end in that type of situation. Um, so we looked last time and we're working backwards. Mods 1, 2, and 4 have non-parametric equivalencies. So mod 4 is working backwards from the ANOVA test, doing something called the Kruskal-Wallis. That's in the last video, and it went over what this is all doing. Then mod 3 did not have a non-parametric technique, but mod 2 does. And mod 2, sorry, checking my recording on. Mod 2 is about another type of correlation called the Spearman rank correlation, which even though the example that Blumen does not actually need, Spearman rank correlations can be done on rank data, like when you have a marathon, running first, second, third, and then like maybe like the, I don't know, rank ages of something like that or some weird thing. But you can use rank correlations when you do not necessarily have discrete or continuous data because they can be done ordinal data, which is kind of a cool thing to be able to do. Um, even though this example does not explain that. So rank correlations are literally done on ranks. A lot of non-parametrics is done on ranks. Like, so this data here, like the lowest number of branches is rank 1, and then the next lowest rank 2. Ranks, literally, like, first, second, third, they're ranks. Um, and then the statistics are actually done on those ranks. A lot of non-parametric stuff does that. And then this correlation is done actually on the differences, and then you calculate it using this formula here. And yeah, only the actual algebraic calculations in both these cases, in both the Kruskal-Wallis and the Spearman rank, you do not get a p-value with the associated test statistics. So SPSS, you still need that to get these p-values because you always want to know something significant, people. That's always the 0.05 cutoff. Okay, so this final video, we're gonna actually go back to mod 1, which was January, and it was cold and snowy and freezing. And by the time you watch this video, it will be at least the last week in April, beginning of May. So way different world. Anyways, there are actually two tests we're going to review from mod 1. The first one, this is a crazy world of nonparametrics. Like, there's so many different names for things. I think there should be a law against redundant naming, but I call this the Mann-Whitney test. It's also called the Wilcoxon rank sum test, which I don't like because the next test we're going to use is actually the Wilcoxon sign test. So don't call it this. Call it the Mann-Whitney test, but you will see the same test with different things. Now, one of the assumptions of a means test is that our sample means come from a normal distribution, but what if they don't? What if the data is not normally distributed? So the answer is you can use the Mann-Whitney test. Okay. Yeah. Anyways, and this is just the specifics of how this is calculated, and this is how the z-score. Now, somehow this test actually does end up using a standard normal score as the test statistic. I don't remember exactly how. I don't think it's in Blumen either. But anyway, so here's the example. Time to complete an obstacle course. We have the Army and the Marines. And two independent samples. Again, this is the independent sample one. Okay. Remember from two sample means tests, there was independent and dependent. We're not going to do a dependent equivalent. It's going to look like we're doing what we're not. So this is the independent, two separate groups, Army, Navy, or Army, Marines. They don't overlap. The same person can't be in both. So these are two independent samples. And the question is the time that it takes them to complete an obstacle course. Is there a difference between the Army group and the Marine group? Okay. Again, Blumen is giving an example that I'm not 100% sure they actually need a non-parametric statistics for. They are small sample sizes, but everything in Blumen's a small sample size. So hey. But we want to compare whether the average time in the Marines is different than the Army. So we have like mu of A equals mu of M, and this is our null hypothesis that we're testing against. Okay. The hypotheses actually don't change for the non-parametrics. Like, your hypothesis is the same thing. It's just the technique you're using is not using the underlying probability distribution. You're using this kind of like heuristic distributions. Yeah. Hypothesis, no difference. Alt is that there is. And then we have how this one works. And at first you look at this like, what is that doing? It is ranking. The lowest time is 8 minutes, and that's a Marine. That's what you're seeing here. So this right here, the lowest is the Marine, the next lowest is the Marines. So that is what we're looking at with this kind of like funny looking chart. The other thing about this chart, I don't know if you noticed it. At first I was like, why are these even when these are not even? And the answer is like they did this clever spacing to make them look even, but they're not. Um, so the lowest one is Marines, 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 Marines. It looks like the Marines are winning, and their times Marines, Marines. And then we have an Army one, and then we have these kind of weird looking ones. This is because you have a tie, and then so the way that it's ranked is rather than 7, 8, 9, 10, it's like 8.5 because you're like averaging those. That's why you see these like average rank thingies in there. But anyways, you're taking every single time and ranking it. This is just like if you look at the timeline, no pun intended. 8, 9, 10, blah 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 blah. Like this is like, these are like times going up, and then they're just associating the groups and then the ranks. Then we have this weird thing that we do where we sum the ranks of the group with the smaller sample size. Um, I don't know where that one came from, but it works. So the smaller sample size is the Marines right here because they have fewer values. And apparently 93 is the sum of the Marines. 1 plus 2 plus 3 plus, yeah, this is all these numbers here. So we are summing the ranks of the Marines. Again, voodoo. I don't know exactly, these are pretty old things. Like somebody like before major computers sort of spent probably years like thinking through this and published it stuff. But anyways, so that's what they're doing. And then we come up with some values. I don't know what it's a mean, but these are like sample sizes mean. I don't know exactly how they're getting this sort of mean and standard deviation metric that they're getting using just sample sizes. I don't know. I don't entirely understand that. But anyways, when all is said and done, they calculate a test stat, which is a normal score, which is really weird. But it works. And we get the sum of the ranks. Now, importantly, this right here, this R thing, this is this 93. And then they're just plugging in 93 minus this algebraically calculated mean minus or divided by this algebraically calculated standard deviation. And we get a test statistic of negative 2.41, which your standard normal, and minus 1.96. And you know that this one, in this case, your p-value is going to be less than 0.05 based on that, because your standard normal scores, because you've been in stats classes for a long time now and you know that. But yeah, so this one, that's a win. We know how to do that. But we still want to do this in SPSS because we want to know how, because you're going to have a homework problem and a test problem doing this. So this is the output from SPSS that I'm going to run in a minute. And you can see this is the 93 sum of ranks for the smaller sample size. This is what's in that formula. And this is the z-score negative 2.04. Well, they rounded it or something, but it's darn close. And then the associated p-value here is 0.016, which is below 0.05. So yes, there is a significant difference between the average of the Army and the average of the Marines on the obstacle course. And that's how to interpret this. By now, you know how to look for asymptotic significance. Anything that's a significance, that's your p-value. Okay. Yes, so now we need to go into SPSS and run this Mann-Whitney test on 2 independent samples for testing means when you don't meet the assumptions for t-test. Okay, so this is an SPSS and it's called obstacle. Okay, now, once again, I entered this as string and I had to do automatic recode, which I already did, so I can't do it again. Well, I could, but I'm not going to. And I had to go under transform automatic recode. That's that magic thing that takes a string variable and turns it into a coded numeric variable with labels, which is just magic. And so this is the original string variable, and then this one, Army is 1 and Marines is 2. So those are the values associated. Okay, so that's how the data is set up, just like a regular old t-test. And to run this, we're going to go to Analyze, and we are going to go to Nonparametric Test, to Legacy Dialogues, and we're going to go to the 2 independent samples. Okay, this one right here. Yeah. Again, I think this one probably does it too, but I'm not gonna I'm going to do the way that I know because I'm not feeling super adventurous. So, two independent samples, and it looks and smells pretty much exactly like the two independent t-test. But it's not. It has Mann-Whitney checked off, which it should. Again, this non-parametrics world, like literally I told you the story though, like I used to have this book. It got moldy, so I threw it away. I had this non-parametric statistics graduate book, and it had like pages and pages of like names and tests and tables. Honestly, I never really used this. There's a lot of stuff in stats I use. Like, I mean, professionally, I used like correlations and plots. I use regression up the wazoo. I use basic means test up the wazoo. I don't think I ever used a non-parametric test. I mean, mostly, I worked in medicine and stuff, but so that's part of why when I do this unit, I'm kind of like, oh, okay, well, let's teach that to the psychology students, even though I might use it. But anyways, down here, test type, there's actually like 5 different variants of this. I don't know. There's probably even more. There's 4 in SPSS. But anyways, the test variable is time, and then the grouping variable is not the original string variable, but the transform variable, which I go under here. And just like always, SPSS for some reason cannot pick the groups up. You have to actually type in 1 and 2 in order for it to run the test. I don't know why. It was just never reprogrammed like to make it better. Hit continue and then hit go. And we get this. Yay! And this is exactly what you'd expect because it looks exactly like the slide. So it gives us the sample sizes, it gives us the mean ranks and the sum of ranks. This is that value that's in that weird computational of the test statistic that I don't entirely understand. And then we have our test statistic, which these values here, 27, this is like in the old days, if you looked it up in a table, you would get the p-value from that. But anyways, and we also get a z-score somehow for this test. But what's super important is the p-value is 0.016, which is less than 0.05, which means we conclude there is in fact a difference between the two groups, Army and Marines. Awesome. I might have said Navy once, but I don't know. I always think Army, Navy, just Army, Marines is just different. But anyways, okay, so that is almost the last test. There's one more, and we can all celebrate because this is the very last test. I'm going to teach you new and fresh, and then you're on your own. Okay, so we are in the slides, and we have one more test. The final test is something called a sign test. This is the parallel of the one sample means test. We just did the 2 sample independent test. We're not doing a 2 sample dependent test. This is the sort of equivalent of the 1 sample means test, which is when we were just comparing a null value to like some hypothesized value. This is usually the first test you learn, at least in our courses. And you're just comparing whether or not your data maps to this value. This test, however, we're actually going to run on the median, not the mean. Remember that the mean is sensitive to outliers, but the median is not. So that's one reason why this would actually be a legitimate reason to use this if you were doing something like income, which is like skewed and not like, and you have a small sample size. This is actually a test that you might want to use instead of radio test. But anyways, and this one I call it the sign test. Yeah, I just call it the sign test. Just call it the sign test. That's the easiest thing. We look like, why is it called the sign test? You'll see. Okay. What you do with the sign test literally is you compare your hypothesis to a claim value. Now, the claim value is a median, not a mean, but it's still a measure of central tendency. So your hypothesis is that your median is equal versus your alt is that it's not equal, because this is always what you're testing against, and really the alt doesn't really you're always testing against your null. But anyways, and then compute this, make the decision, summarize the result. Same thing always. I forgot to put my little tier-D thing in here. But claim, data, decision, same. That's a terrible rendition of my nice little diagram. But anyways, so here is the example for this. Patients at a medical center. The manager at Grand Valley Medical Center claims the median number of patients is 80 per day. That's a lot of patients, man. Anyways, to test the claim, 20 days are randomly selected, and the number of patients seen is recorded. Oh, seen by doctors, plural. Okay, phew. I'm like 80 patients a day, really? So this is the data. Yay. Now, what do you do with this data? And the answer is you type it in a big column in SPSS, and it will look like this. Okay. And you're like, this is what it looks like. Like, where's the 80 go in? Here's what's really super weird about this test. there's a lot of weird things about, like, half of what I'm teaching this course literally is like how to do the weirdness in SPSS. And that really sort of like makes it like more challenging to do the statistics, because really you have to pay a lot of attention to like how you're running things and how you're setting them up. And the answer to, am I just going to give you the data all set up, is no. However, on your final, I'm not going to, like, you're not going to have to restructure the data. Like, you're good. Yeah. So the claim is that the median is 80. Okay. So we're testing against somewhere. I lost the slides. We're testing against the median being 80. Okay. And I don't know why my computer does this. Like, it just keeps doing that. But anyways, and you're like, why is it called the sign test? Because literally what you do, if you're doing this manually, is you have your data and you have your median, and say your data is like 78, 82, 90, whatever, and your median that you're testing against is this. It literally is testing against signs, like negative, because this is this below this is negative, choose negative, positive, positive. So sign means plus or minus. And literally, you're doing a sign test. Okay. That's why it's called the sign test. If they're equal to each other, you assign 0 and it basically gets ignored. Okay. And what it's literally doing is like adding up the number of pluses and minuses and like determining whether or not, like, if you think about this, if the number of pluses and minuses are basically even, then your median is basically, like, your null hypothesis is basically correct. But if the number of pluses and minuses is like substantially off from here, like you have way more minuses or way more pluses, then you're going to get a significant result. It's really that simple. And of course, we actually do want to get like an actual test statistic and stuff and a p-value associated with it. But conceptually, a sign test is just looking for the data minus the median, and it's looking for whether it's plus or minus. And if there's like a huge discrepancy in these, like, you know, obviously if you're, you know, you will have a significant result, because like if a lot of your data is positive, you'll have a significant result. If a lot of your data is negative, you'll have a significant result. If there's pretty much a balance, you won't have a significant result. That's how the sign test works. That's all there is to it. Anyways, and then this is the manual directions, and then interestingly, I didn't finish the slides to show you how it did in SPSS, but I'm going to show you that live, so we're good. So the data is in SPSS. This is the data. Trust me, it's the same data. And we're testing against a median of 80. And then you're like, well, how do I run that? Can I go under Analyze? And can I go to Nonparametric Test? And can I just like run it? No. Because life is never going to be that simple. The way that you have to run this, like, you would think that it's one sample and you could just put it in here, but this is not a median test. You can't do it in here. So what you have to do, and this is just plain weird, this is really seriously weird. What you have to do is you actually have to type an additional column, and you have to put this like fake median in here. Variable names cannot contain an illegal character. All right. So what you have to do to get this thing to run, and don't forget this because you will not guess this one. You have to create this column, and then yes, you have to like type all the way down, and you have to type all the numbers in, which I know is a pain. I feel for you, but that's part of the job. So hey, you're being paid with degrees. So I'm gonna sit here and boringly type numbers in, and you have to do this for all of them. Luckily there's only 20, because if there were more, I'm pretty sure that I would absolutely bore my viewers to death watching this. But you have to do this. I don't know why. This is just how SPSS is set up. I think it's ridiculous, but you do. Okay, so I have my data and I have my median. I do not, however, have to actually manually calculate out the signs. That SPSS will take care of. So how do I actually run this thing? I go under Analyze, I go to Nonparametric Test, I go to Legacy Dialogues, and I go to two related samples, which again, I don't think you would ever guess because it doesn't even make any sense to me. Has anybody taken inventory of the number of things in SPSS that make no sense? But it's under Legacy Dialogues, two related samples. It's sort of mimicking a paired t-test, but this is not pairs. This is comparing data to a median. And then you get something that looks and smells a lot like a paired t-test. Now, I was playing with this before, so there's defaults in here. And then test type sign. So all you have to do is enter your test pairs. It doesn't really matter which way you do them because you're looking for like it's calculating difference. So median minus that, just enter them all. Make sure sign is checked off. It is by default. Hit go. And you get this. And all you get in your output is the number of negatives and number of positives. Now there's 20, so there's 20 pairs, or there's 20 like data values. 2 of them are equal to 80 apparently, because those are the ties. 15 are minus, and then 3 are positive. You can see from this that you're probably going to get like a significant result because there's like way more negatives than positives. And down here is your p-value, which is like the world's easiest SPS output ever because it is absolutely nothing except the p-value, which is 0.008, which is less than 0.05. And so your conclusion is that you are significantly different than 80. Okay. And you could play with this and figure out why, but I'm not going to because that's not really the point. So back here in this example, you conclude that you are significantly different than 80. It looks to me like they're below, well, I don't know. I'm not going to say anything because I haven't done an additional statistics, but you are significantly different from that median value, and that is our last test. Well, I hope you enjoyed this. So what's remaining for you is the problem set for Mod 5. Everybody has to do that regardless of whether or not you're taking the test. The test for Mod 5, if you've taken 4 tests and gotten satisfactory scores, it's going to be finals week. You have a lot to do. So if you want to take that test, it's a fairly easy test. You can't lose because I'm going to drop the score if you know. And then the final will be open the last week during finals week, and it's due on Friday. And that's it, folks. I hope you had fun. I will see you perhaps in the future. Bye.